Welcome to the Mathematics of Thinking. In this playlist, we'll be diving into famous variety of algorithms. We'll be breaking them down into visuals and in order to understand how they empower every tool we use every single day as a data engineer. So yeah, let's get started. Previous episodes covered everything from graph traversal to signal processing. Today we enter distributed computing, and this one is directly relevant to your daily work as a data engineer. Today we'll be talking about MapReduce, the pattern invented at Google in 2004 that made big data possible, the engine behind the Hadoop, the mental model behind Spark, and the reason a cluster of 1,000 commodity machines can count 1 billion words in a minute. By the end of this video, you will understand exactly how it works, and you will see why every SpicePack job, every Hive query, and every large-scale ETL pipeline is built on this idea. So imagine imagine yourself trapped in this situation. You need to count every word in all of Wikipedia, 20 billion words, 6 million articles, every word counted, every occurrence tracks. On a single machine, this would take days. Your RAM would run out. Your disk would be the bottleneck. Even if you had the best hardware available, you would be waiting. But you have access to a cluster of 1,000 commodity servers, not supercomputers, just regular machines. If only you could split the work across all of them, each handling a fraction of the data, all running simultaneously. The challenge: how do you coordinate 1,000 machine, and how do you split the input? How do you combine partial results from different machines without I'm sorry. So as I said, like, if only you could split the work across all of the machines. So how do you split the input? How you combine partial results from different machines without corrupting the output? How do you handle machine failure mid-job? You do not want to write all that coordination code yourself. You want to write just the business logic, the word counting part, and let the framework handle the the rest. The solution is a MapReduce invented at Google in 2004, published as a paper open source as Apache Hadoop, and today it underpins every large-scale data processing system, from cloud data warehouses to machine learning pipelines. So so MapReduce has 3 phases. These 3 phases can solve almost any large-scale data problem. Phase 1, map. Map is writing a function that takes one input record and emits 0 or more key values pairs. Each mapper runs on a different machine, fully parallel, no communication between mappers, no shared states, pure function, easy to scale. We have the phase 2, the shuffle and sort. You write no code for this. The framework automatically groups all emitted values for the same key together, all the one pairs from all mappers, and end up in the same place. Keys are sorted, results are grouped. Phase 3, reduce. You write a function that takes a key and all its values, a list, and produces a final result. Reducers can also run in parallel, one per key group. Look at the bottom panel. The classic example is input the cat set on the map, output 6 word 1, pair, reduce, output the 2 cat 1, set 1, on 1, mat 1. So this is a word count that's a word count the hello world of MapReduce, but the same pattern counts web page reviews, aggregates sales data, computes page rank, and train distributed machine learning models. So for now, let me show you how Hadoop actually runs a MapReduce job. So I have 3 components. It does the thing she's designed for. We have the HDFS, the Hadoop distributed file system. Your input data space into 128 megabytes blocks and distributed across data node machine in the cluster. Every block is replicated 3 times on a different machine, so if one machine dies, the data is not lost. The name node keeps track of which blocks live on which data nodes. The most important principle in Hadoop: move computation to the data, not data to computation. Instead of copying your Wikipedia data to your processing machine, Hadoop sends the mapped code to the machine where the data already lives. Network traffic is minimized. We have the yarn component, which is yet another resource negotiator. This is the cluster operating system. The resource manager knows how much CPU and RAM every machine has available. When you submit a job, yarn's application master schedule your map tasks on a specific data node where is your input blocks already live. And in the MapReduce job itself, you write exactly 2 functions, the mapper and the reducer. You package them into a jar or a Python script. You submit the job. The framework handles splitting, scheduling, shuffling, fault tolerance, and output collection. You write 0 infrastructure code. And now, let me trace through a complete MapReduce job on a small example. We have 3 documents, each like 3 machines, and machine 1 has the catsat, machine 2 has the cat8, and the machine 3 has the matsat. So the input split, each machine already holds its data, no movements needed like for the map phase. This is the data locality principle in action. Map phase, each machine runs the mapper independently, and in parallel, machine 1 emits the 1, the cat1, sat1, machine 2 emits the 1, cat1, ate1, etc. So all the 3 mappers run at the same time, no waiting. Combiner, this is optional but important before sending results over the network. Each machine runs a local mini reducer. Machine 1 combines its output, saves network bandwidth. We will see just how much on the next slide. Shuffle and sort, the framework takes over all values for the word D from all the 3 machines and are routed to the same reducer. All values for cat to the same reducer, all values sorted alphabetically: 8, cat, mat, sat, D. Reduce phase, each reducer receives its key and its all values. The 1 1 1 sums to 3, cat 1 1 sums to 2, sat 1 1 sums to 2, 8 1 stays 1, mat same stays 1. So the final output written to HDFS. So now let me show you why the combiner is the most important optimization in any MapReduce job. So without a combiner, imagine processing Wikipedia. One machine processes 1 million occurrences of the word D. The mapper emits D1 1 million times. All 1 million pairs are sent over the network to the reducer. That is 1 million small network messages for a single word. Across the entire Wikipedia dataset, this is catastrophic. The network becomes the bottleneck. Jobs that should take minutes take hours. With a combiner, same scenario. Before sending anything over the network, the machine runs a local mini reducer. 1 million the 1 pairs become a single D. 1 million pair. 1 pair goes over the network instead of 1 million. So look at the right panel. The reducer receives like 1 million instead of a list of 1 million ones. Same answer, same correctness, 1 millionth of the network traffic. In practice, combiners typically reduce network traffic by 14 to 19%. They are not optional in production, they are mandatory. Critical constraint: the combiner must only be used when the operation is commutative and associative. Sum is safe, count is safe, max is safe, min is safe, but average is not safe. You cannot average partial averages. For average, track sum and count separately, then divide at the reducer. So so here is a complete MapReduce pipeline in Python for functions. 1 orchestrator. The mapper is a pure function. It takes a document string, splits it into words, lowercase each word, and returns a list of word 1 pair. Pure function, I mean no side effects, no shared state. This is exactly what makes it easy to parallelize. we have the combiner function that takes the mapper output and aggregates locally using default dict for each key and value pair. It increments the counter, returns the combined list much shorter than the input. We have the shuffle and sort groups all values for the same key using another default dict, then returns a sorted dictionary in Hadoop production code. You never write this, the framework does it for you. We have the reducer, it's trivial, take a key in the list of values, return the key and their sum. And we have the orchestrator, uses process pool executor, which is a Python built-in multiprocessing to run mappers in parallel. In production, you replace process pool executor with a Hadoop or a Spark cluster. The mapper and the reducer functions stay identical. This is the power of the pattern. The business logic is completely decoupled from the infrastructure. You write word counting, the cluster handles the distribution. Now, let me show you where MapReduce lives in the systems you work with. We have Google's original use case indexing the entire web. The 2004 Google paper described using MapReduce to process petabytes of web crawl data to build the search index pattern. The algorithm that covered in episode 3 was computed as a series of MapReduce jobs. Log processing at scale. This is the most common enterprise use case. Parse and aggregates terabytes of server logs, counts HTTPS or errors, extracts P95 latency, metrics, detects anomalous IP addresses, all distributed across a cluster. We have the ETL pipelines with Hive and Pig. We have Apache Spark. The 6-user Spark generalizes MapReduce with the in-memory computation instead of writing intermediate result to the disk after each phase. With Hadoop does, using HDFS, Spark keeps them in RAM for iterative algorithms like machine learning. This makes Spark 100 times faster than Hadoop. So we have cloud managed services, AWS, EMR, Google Data Proc, and Azure HD Insights, all run managed Hadoop and Spark clusters. ML at scale with Mahot and MLlib, matrix factorization for recommendation, k-means, clustering, and collaborative filtering, all decompose naturally into MapReduce jobs. MLlib, Spark implements these as distributed RDD transformations. So two numbers again, map phase per node, O of n over P is the total number of records. P is the number of parallel mappers. Adding machines reduces the time proportionally. This is horizontally scalability, the core promise of MapReduce. Shuffle and sort O of n log n. All emitted key value pairs must be sorted across the cluster. This is always the bottleneck in MapReduce job. If your combiner is working well, n here is much smaller than the raw mapper output. We have three limits: disk, entry, output. Bottleneck, Hadoop writes to disk after the map phase and again after the shuffle. If you chain multiple MapReduce jobs together, you read from disk and write to disk at every step. For iterative algorithms, this is catastrophic. Use Spark, it keeps everything in memory. Not for small data. A MapReduce job takes 13 to 16 seconds just to start. Job submissions, resource or negotiation, task scheduling, and output collection for a 10 MB files. A single Python script on your laptop is 100 faster. MapReduce is for terabytes and petabytes of data. Combiners are not always safe. Only use a combiner when the operation is commutative, associative, like sum, count, max, mean. All safe. Average is not safe. Computing average on a partial result gives you the wrong answer. Track sum and count as a separate keys and divide in post-processing. So, 4 things you know now. 1. MapReduce splits any big computation into 3 phases: map for parallel transformation, shuffle and sort for automatic key grouping, and reduce for parallel aggregation. 2. The combiner is the most important optimization. Run a local mini reducer on each machine before the shuffle to reduce the network traffic by orders of magnitude. Only safe for commutative and associative operations. 3. Hadoop runs MapReduce on HDFS via yarn. Your job: write the mapper and the reducer. The framework handles data splitting, task scheduling, network shuffling, filter length, and output writing. 4. Spark generalizes MapReduce with in-memory DAG execution, 100 times faster for iterative workloads, but MapReduce is the mental model behind all distributed computing. Understand it first, everything else becomes obvious. So drop a like if this was useful, and tell me in the comments, have you written a PySpark job where you realize you were writing a MapReduce without knowing it? The moment of recognition is worth it writing about. So in the next episode, we'll be talking about the Bloom filter. How do you check if a username exists in a database of 500 million users in constant time using almost no memory? The answer is a probabilistic data structure that will genuinely surprise you. So see you there. By the way, if you are new to Python, I'm launching a Python formation. You can subscribe by filling the form in the description.